So, we talk about dynamic programming, which we have seen earlier also we have started. So, we will talk about more on dynamic programming. So, it is very exciting topic. So, dynamic programming, in short, it is called DP. So, it is basically a very powerful general powerful design technique. So, so it is basically a powerful general design techniques to solve the problems. Algorithmic design technique. Okay. So, basically it is a careful brute force. So, DP is basically careful brute force or exhaustive search. So, in exhaustive search the time is exponential. So, we look at the all possible solutions. Okay. So, that is called exhaustive search or brute force. So, that is the exponential algorithm, but we reduce that exponential space to the polynomial space carefully. So, that is the technique of dynamic programming. So, it is basically we reduce this exponential space to a polynomial space. So, that is the idea. So, it is specially good for kind of optimization algorithm, like if there is a shortest path. So, dynamic programming is very much useful for optimization algorithm. So, it is basically, so we have a problem, we reduce this problem in a sub problem. So, by recursively. So, this is basically sub problems, we have to get the sub problems and then we reuse the sub problem. So, this is by recursively. So, this is the recursion. So, recursion and then we reuse the sub problems to get the we reuse the value of we reuse this value in the whole problem. So, this is the idea. So, basically we discuss this through some example like problem like finding the Fibonacci number and then the shortest path problem. Okay. So, let us just start with the Fibonacci number problem. So, finding the nth Fibonacci number. So, this we have discussed already in the beginning of our this course, like when we start the divide and conquer approach. So, there we have discussed this. So, just to bring this problem and we will see how we can solve this using a dynamic programming technique. Okay. So, here is the definition of the Fibonacci number problem. So, Fibonacci numbers. So, what are the Fibonacci numbers? Basically start with 1 1, then 2, then 3, then 5, then 8. So, sum of previous 2. So, this is basically it start with say f 1 is 1, which is same as f 2, and then f n is nothing but f n minus 1 plus f n minus 2. Okay. So, this is the formula. So, our goal is to find the problem is to find the nth Fibonacci number, nth Fibonacci number, that is f n. So, this is the problem, we have to find f n. So, n is an input, say we have to find f 2017. So, n is 2017. So, this is the problem. So, finding the nth Fibonacci number. So, what is the naive algorithm to solve this problem? So, what is the correct algorithm to solve this problem? So, you have to use this recurrence. So, you have to use this formula. So, this is the naive algorithm. So, we have to follow the recursive formula, like, so suppose we want to find, this is the call. Now, if n is less than 2, we return 1. So, this is the base case, otherwise else. So, else what we do? We compute f of fib of n minus 1 plus fib of n minus 2, and we return f. Okay, so, this is the correct algorithm. So, to compute the Fn, nth Fibonacci number. So, this is the recurrence, this is the recurrence. So, this is coming from the definition of the Fn. So, this is the recursive definition, okay. And this is what is called base case. So, now what is the time complexity of this algorithm or of this code? So, time complexity, this is exponential algorithm. Why? Because if T n is the time to time for this, then T n is basically, we have to call T n minus 1 plus T n minus 2 plus theta 1. Now, why this is exponential? This is basically we can write as greater than equal to 2 T n minus 1 plus theta of 1. So, this will again give us greater than 2 to the power n by 2. So, this is basically exponential algorithm. Okay. So, now this is a exponential time algorithm. Now, we want to use the technique which is called dynamic programming technique to reduce this exponential algorithm to the polynomial time algorithm, like linear algorithm. Okay. So, it is a so we will use two techniques to do that. One is memoized DP algorithm, another one is bottom up DP algorithm. So, first let us start with memoized DP, because this is exponential, exponential is bad. So, we want to reduce this, we want to use the DP technique to reduce this time complexity from exponential to polynomial. So, this is the first technique we will use, memoize DP algorithm. So, memoize means we remember. Once we compute a value, we remember. So, we will use a dictionary, we will put the value over there. So that we do not need to compute it again. So, that is the memoization, remembering. So, we remember the value. So, this is basically remembering. Okay. So, we remember the value. So, what is the, how we remember? We use a dictionary, once we compute the value, we put it into dictionary. Now, when we look at the dictionary, if the value is there, then we will get that, otherwise we have to compute it, and once we compute it, we put it into the dictionary. So, that is the memoize, that is the remembering. So, suppose this is our dictionary which is empty initially, and say this is the code, and now we are computing fib of n. Now, if n is not in the dictionary, if n is in memo, then we return memo n. So, this is just a kind of table lookup we do. Else, if then the code is similar to earlier, this is the recursive call. else if n is less than 2, then f is equal to 1, else we compute, we call phi of n minus 1, phi of n minus 2, and then we put this into the memo and we return f. We return f. So, this is the recursive step, same as earlier, but here we are just look at the table, we are just look at the dictionary. So, if that is in the table, then we are just not computing that, otherwise we are computing that. So, this type of technique we can use for any recursive algorithm, this kind of. So, let us look at the recursive tree for this code. So, suppose we want to compute f of n. So, to compute f of n, we need to compute f of n minus 1, f of n minus 2. So, in order to compute f of n minus 1, we need to compute f of n minus 2, f of n minus 3. So, here also we need to compute f of n minus 3, f of n minus 4. So, like this, again we need to compute f of, say, f of n minus 2 means f of n minus 3, f of n minus 4, f of n minus 4, f of n minus f of n minus so minus 1. So, f of n minus 4, f of n minus 5, like this. So, this is the exponential time algorithm. Now, here if we look at this tree and this tree are same, and this tree and this tree are same. So, there are many sub problems are going on. So, this is one of the hallmark of dynamic programming technique, dynamic programming problem. So, if we have many sub problems. So, by once we calculate this, because here we are again calculating this. So, once we calculate this, why to calculate it again? So, to avoid that, we are going to memorize that, we are going to remembering that value. So, we are going to store into the table. So, that is the idea. So, this way we are saving the time, otherwise this will be exponential. So, this is the technique. So, we are memorizing, we are storing this, once we calculate this, we are storing into the dictionary. Now, once we are going to calculate this, we look at the dictionary, since we got it, we will not execute this calculation. So, that way we are saving the time. So, basically how many non-memoized call we have to do? So, number of non-memoized. So, number of non-memorized call is basically so we have to calculate this f1, f2 up to fib n. So, n times. So, number of non-memorized calculation this is n times. Now, for memorized calculation, so that is the non-recurrence. So, non-recursive call. Non-recursive call is basically takes theta of 1 times, because we have already calculated this. So, now what is the total number of what is the time complexity? Time complexity is basically theta of n. Okay. So, time complexity is basically theta of n. So, this is basically is telling us, this is basically time is basically number of sub problems into the time to solve each sub problems. This is amortized analysis, because Few sub problems we are calculating that by adding, but few sub problems we are getting from the lookup. So, that is the way. So, basically we are just adding these two. So, this is basically time divided by sub problems. So, this is basically time per sub problems, and time per sub problems is theta of 1, because we are just looking at the table to get the value. Okay. And this is n. So, that is why it is coming to be theta of n into theta of 1. So, this is basically theta of n. So, this is the theta of n times algorithm for solving the to getting the Fibonacci number. Okay. So, now we will look at another approach, which is instead of instead of putting everything into the dictionary, we will look up what is called bottom up DP algorithm. So, this is basically bottom up DP algorithm. So, let us just before that let us. So, DP is nothing but recursion plus memoization. Okay. So, basically idea is we memorize or remember we remember the value which we have already calculated, and we reuse the solution to the sub problems. So, that is the to the sub problems. So, basically, so what are the sub problems in Fibonacci numbers? So, this is basically f1, f2 up to fn. So, these are basically our sub problems. So, there are n sub problems, and to solve each sub problem it is taking constant time, because we are just looking at the table and then getting the value we are adding. So, theta of 1 time, and there are n sub problems. So, that is why it is theta of n. So, this is the linear time algorithm. Okay. So, now we will look up the another approach, another DP approach, which is called bottom up DP algorithm, where we just store the last two value instead of putting everything into dictionary, because we just need the f of n minus 1 and f of n minus 2. We do not need to store the whole dictionary. So, that is the idea. So, this is called bottom up DP algorithm. So, what we are doing here, this is the code. So, we have this empty set. Now, for k in the, this is the range of the k. So, range of the k is basically 1 to n. We are calculating f n. So, our range is 1 to n. So, now we have the recursion, that recursive formula less than equal to 2, f equal to 1, else f is f of fib of k minus 1 plus fib of k minus 2. And then fib of k is basically f, and we return fib of n. Okay. So, this is basically, so this part it is basically theta of 1 time. So, this is basically we are just storing last two value. So, this is the bottom up way. So, we start calculating f4. So, we basically start calculating f1, f2, then f3, f4. So, always we store the last two value like this. Okay. So, we keep on calculating this way and we ultimately we return this. So, this is the bottom up way. So, we start with f1, then f2, then f3. When we call f3 we forgot f1. So, this way. So, fk is basically fk minus 1 plus f of k minus 2 this way. Okay. So, every time we just store last two value of the Fibonacci number and then we add it up to get the next value. So, when we stop at fn. So, this is a linear, this is basically size, this is theta of n times algorithm. This is the same time complexity as the memorize DP algorithm, but this has the advantage that the space complexity is less, because it has we are, so for memorize we are putting everything into the dictionary. So, that size is less. So, exactly same computation, but less space. So, this is practically faster because there is no recurrence. Now, we want to see some topological ordering for this computation of fn. So, like this is say fn. So, to calculate fn we need to calculate f of n minus 1, f of n minus 2. So, f of n minus 1, f of n minus 2. Now, to calculate f of n minus 1 we need to get f of n minus 2 and f of n minus 3. So, and then to calculate f of n minus 2 we need to get f of n minus 3 and f of n minus 4. So, this way dot dot dot. So, this is basically a topological sort. Sorry, this is basically a topological sort of sub problems. So, these are the sub problems dependency graph. Dependency acyclic graph. Okay. So, this is basically the DP approach for this problem. So, this is giving us this. So, the naive approach was exponential, but we reduce this into polynomial time algorithm. So, this is basically linear time theta of n. Now, so we have seen this problem can be solved in log n. Who can remember this? This problem of finding the nth Fibonacci number. So, how to get nth Fibonacci number? So, we have seen this in the divide and conquer technique in the earlier beginning of the course. So, we have seen this f of n plus 1, f of n, f of n, f of n minus 1. This is basically 1 1 1 0 to the power n. This kind of formula we have seen. So, this is basically kind of powering a number, powering a matrix, but this matrix is a constant matrix. So, once we have a constant matrix, so this is some sort of a to the power n, but A is a 2 by 2 matrix, just a 2 by 2 matrix. So, it is kind of same as powering a number. So, it is basically we have the divide and conquer formula for this. This is basically a to the power n by 2 into a to the power n by 2 if n is even, otherwise a to the power n minus 1 by 2 into a to the power n minus 1 by 2 into a if n is odd. So, this is the divide and conquer steps. So, now, we have a problem of size n, we reduce this problem into sub problems of lesser size, and then what is the recurrence? Recurrence is basically T n is equal to, so only one sub problem T n by 2 plus theta of 1. So, this will give us theta of log n. So, this we have seen in the divide and conquer technique class. Okay. But if we use the DP, we can solve it using. So, DP is a general technique where we can reduce a exponential time algorithm to a polynomial time algorithm. So, that we will use for many problem, many optimization problem can be reduced in the DP technique. So, in the next class we will discuss another problem which is called shortest path problem, and we will see how we can use the dynamic programming approach to finding the single source shortest path. Thank you.